Hello everyone, welcome. This is paper 2 from November 2025 and this is time zone 3. Let's have a look and see what we can do. Question 1. A marathon is a race over a distance of 42.19 kilometers. Part 1 of A asks us to write down 42.19 kilometers correct to the nearest kilometer. So the nearest kilometer would be to this ones place right here. Here we have 0.19, so in this case we would round down to 42 kilometers. Write down as a command term just means provide the answer, no process needed. Part 2 of A, find the percentage error if 42.19 kilometers is rounded to the nearest kilometer. So in this case we want the percentage error of the difference between 42, our estimate, and the exact value of 42.19. So we have percentage error in the formula booklet. I'll go ahead and bring that up. Number in algebra. And then here it is, just right at the bottom, percentage error. What this is telling us, we have estimate minus exact over exact. And then we have these absolute value bars, which essentially say no negatives. So we just want the absolute difference. And then we multiply by 100%. So let's write this out and then we'll substitute and solve for this question. All right. So let's write it out here. I'll write it out using complete words just to, I guess, illustrate what's going on. So percentage error, I guess I won't write that, but this is epsilon. And then we have estimate minus exact over exact. We want to close these absolute value bars. Remember, these things say no negatives. Whatever happens on this inside, we just want the absolute difference, no negatives. And we want a percentage, so we multiply it by 100 in the end. All right. So let's go ahead and substitute. Our estimate, we rounded 42.19 to 42. So this is our estimate. I want to make sure these are the correct numbers. Yeah, 42.19. Exact was 42.19 over, and then exact once again, 42.19, and then multiply by 100%. All right, let's just go ahead and find out what that is by putting this into the calculator. So here we are. And let's open up a fraction. So we have 42 minus 42.19 over exact of 42.19. This actually is going to give us a negative value, so we just have to be careful that we don't actually include it. So we have negative 0.04503 multiplying by 100 would give us a percent, and now we have 0.450344%. So I'm going to go back to the document where we don't want any negatives. So this is 0.450 sig figs, and then we'll write percentage. Okay. Rolando and Devi are training to run a marathon. They both start their training in the same week. Rolando runs 6 kilometers in the first week, 8 kilometers in the second week, and 10 kilometers in the third week. In each subsequent week, he runs 2 kilometers further than the previous week. Part B asks us to find the week during which Rolando runs 42 kilometers. This is a 3-mark question, so we're going to need to show some process here. There is one way we could do it. If we could say 6, 8, 10, and we could just keep counting by 2, and then I guess see when we reach 42. But if they tell us that each subsequent week he runs 2 kilometers further, what we have here is an arithmetic sequence. And I guess maybe I'll just say one thing as an aside right now. During the 5-minute reading time, I think it's a good opportunity to kind of see what's going on and in some ways compartmentalize questions, as in what type of question is this? And this is this first question that they're starting off with is a very, very common question. Just looking at it really quick, and I encourage you to kind of have a read through it before working through these in some ways. But this is a classic kind of question where we have arithmetic sequence and then geometric sequence, and then we want to find the intersection of these two. Classic question, comes up fairly often and has come up fairly often. Arithmetic sequence, which is kind of like a linear equation. Geometric sequence, which is kind of like an exponential. And then we find out where they intersect. And in this question, it's actually when one person, I guess, exceeds the other. So kind of compartmentalizing or finding out what type of question we're dealing with during that 5-minute reading time can help make your overall process working through these examinations more efficient. So looking at this once again, arithmetic geometric sequence, intersection of two functions, and then with that in mind, I think we've got a good kind of structure to work through this. All right, so let's go back to this part B here. Find the week during which Rolando runs 42 kilometers. So I'm going to erase this. And we'll work with this arithmetic sequence. I often think for arithmetic sequence, tables are quite good. So I'm going to set up a table just really quick. Here we have n term number, un value. We could have written d here if we wanted, but d is often given for common difference, so I didn't want to confuse it. So 6 kilometers in the first week, 8 kilometers in the second, and so on. So let's write first, second, third, and let's put those values in. 6 kilometers, 8 kilometers, 10 kilometers, and we're told that in each subsequent week it's 2 kilometers further. So let's see if we can write some arithmetic sequence formula, and then we'll use it to find when Rolando runs 42 kilometers. So arithmetic sequence is given by this. un is equal to u1 plus n minus 1 times d. This is in our formula booklet as well. Value of a given term is equal to first term, u1 plus n is just the term number that we want to solve for. And d is the common difference, what we add or subtract to go from one term to the next. So let's find u1, d, then we've got a formula, and then we can deal with this 42 and find out the term number or the week in which he runs 42 kilometers. All right, so let's find common difference first. From 6 kilometers to 8, we add 2. From 8 to 10, we add 2. And that's exactly what our common difference is. What we add or subtract to go from one term to the next. So 2. Value of the first term, u1. u1 is just 6. So let's substitute those values. 6 plus n minus 1. Common difference is 2. All right. So now we've got our formula for an arithmetic sequence, and essentially we've got a function which accepts inputs and outputs. We substitute some value for n, gives us the total value that the person would run, this number of weeks, and reversing that process, if we have 42, we can substitute that output and then find the input. That's going to be our strategy for this question. So let's go ahead and do that. 42 is the value of a given term. And now the question we are asking, what is that n, or week, that would make that true? So 42 is our output. What's the input? What is the week in which he runs 42 kilometers? So we've got one equation here with one unknown. We can go ahead and put this into the calculator and solve, and then solve for n, the term number. So here we are, menu, algebra, numerical solve. 42 equals 6 plus n minus 1. And then our common difference was 2. And we'll ask the calculator to solve for n. So in the 19th week, he runs 42 kilometers. So let's write that out. Going back to the document here. N equals 19. So 19th week, he runs 42 kilometers. One thing I would also say, 3-mark question, they're expecting some process. So showing an arithmetic sequence formula, substituting, and then showing that term number. So if you just write 19, probably just one answer mark, A1. So just be mindful, 3-mark question to show process. All right, part C, find the total distance that Rolando runs in the first 10 weeks. Okay, so I guess the IB was kind enough in this case to bold this keyword, the total distance. Total distance tells us that in the context of an arithmetic sequence, we want the sum of an arithmetic sequence. So if we're adding the first, second, third, all the way to the 10th week, how far did he run altogether? So for this, we'll use the sum of an arithmetic sequence. Just going to draw a dividing line here. This was part B, this was part C. Let's go into the formula booklet and we'll find the sum of an arithmetic sequence. So here we are. So sum of an arithmetic sequence right here. Whoops, sorry, that is the nth term. Here's the sum of an arithmetic sequence. Two different formulas, but they mean the same thing. They're just written differently. They're two different expressions of the same formula. Sometimes one is going to be more efficient than others. So let's look at this. They both start with this n over 2, but in this case, looking at this first formula, or this equation rather, we have value of the first term, number of terms, common difference. Here we have value of the first term, value of the last term. In this case, it would be the value of the 10th term, U10. We don't actually know what this is, so I don't think this one's going to be as efficient. Not to say that we couldn't find it, we certainly could, but looking at this first formula right here, we know U1, we know term number, it's going to be 10, we know the common difference, so we already have everything we need for this formula right here. So let's go ahead and use that. I think it's going to be more efficient. Once again, these are both the same formulas, they're just different expressions of the same thing. All right. So Sn equals n over 2, 2u1 plus n minus 1 times d. All right. In this case, we want to find the total distance that Rolando runs in the first 10 weeks. So we want to find S10, the sum of the first 10 terms. And let's write n for 10. Wherever we see an n, we'll replace it with 10. 10 over 2 plus 2u1. u1 itself was equal to 6. We had that up here as well. So 2 times 6 plus n, number of terms, 10 minus 1. And our common difference, once again, was 2. Okay, so now let's put this into the calculator and we'll solve for the sum of the first 10 weeks. So here we are. So 10 over 2 and 2 times 6 plus 10 minus 1. We could have written 9, I suppose, and then times 2. Okay, that looks good. And the answer is 150, and that seems reasonable enough. 150 kilometers. I'll show actually sigma notation, how to solve this using sigma notation. Sigma notation is something that's on the syllabus, but it's often neglected. It doesn't often show up on the examinations, but I almost feel that's a reason why it potentially could, or it might more so. So let's do this with sigma notation. So here's our sigma notation. This is capital Greek S, sigma right here. And let's write our variable. We want to start from n is equal to 1 all the way up to the 10th term. And it says, okay, I'll take the sum, this capital S, the sum from what? From the first to the 10th term. Okay, and then what is the formula? This is just our arithmetic sequence formula. 6 plus n minus 1 times 2. That was that arithmetic sequence formula that we had initially. So here we have the sum from the first to the 10th term using this formula. It's also pretty efficient, and it's something that's not neglected, but it doesn't have such a big place in the syllabus, but it is in the syllabus. And I almost feel like it's a reason that it might appear more often, or at least in the future. So there it is once again. 150 kilometers, that's the sum that he runs in the first 10 weeks. Last thing I'll say, if you do use this process, if you do use this method rather, your process would be writing out this and then equals 150. Okay. So heading back to the document here. Devi runs 3 kilometers in the first week. In each subsequent week, he runs 20% further than the previous week. These distances form the terms of a geometric sequence. Part D asks us to find the first week during which Devi runs more than 42 kilometers. 4-mark question. Okay. So like I mentioned earlier, this is kind of a classic question. Arithmetic sequence, geometric sequence, and then finding the intersection of these two. So, first part D, find the first week during which Devi runs more than 42 kilometers. We'll solve this using the same process, or similar process as we did for arithmetic, but we'll just use our geometric. So I actually want to draw a table once again. So let's set this up. So I think this is D. So we'll say N, UN, and we'll go first, second, third term, and so. So Devi runs 3 kilometers in the first week. In each subsequent week, he runs 20% more. So first week, he runs 3 kilometers. And then unlike an arithmetic sequence where we add some common difference to go from one term to the next, here we multiply. We multiply by some value to go from one term to the next. So what is that value? We know it's 20% more. One of the common mistakes that students sometimes make is they say, oh, okay, 20% is 0.2. And then when you multiply, for example, 3 by 0.2, you would get 0.6, which means that, Devi is suddenly running much less than he did previously. So we don't multiply by 0.2. Devi is running 100% of what he did earlier, and now he's running 20% more. So he's running essentially 120%, or as a decimal, 1.2 times as much. So 1.2 times as much as he previously ran. So writing that out, our common ratio, what we multiply by to go from one term to the next, is 1.2. And so that 20% extra means that he's now running 3.6 kilometers. And then next week, he's going to run 1.2 times as far. Okay. So, following similar structure to what we had here, let's go ahead and write out our geometric sequence formula. So geometric sequence formula is given to us in the formula booklet. UN is equal to U1 times R raised to the power of n minus 1. So U1, we know what that is. The value of the first term is 3. Common ratio, what we multiply by to go from one term to the next, is 1.2. And then raise this to the power of n minus 1. So now we've got an input-output equation. N, week number, UN, value that he runs within a given week. Okay. Find the first week during which Devi runs more than 42 kilometers. Okay, so in this case, input-output, the output is 42. What is the input? What is the week in which he reaches this value of 42? So 42 is equal to 3 times 1.2 raised to the power of n minus 1. We've got an equation with one unknown. We can go ahead and solve this. So, menu, algebra, numerical solve. 42 is equal to 3, multiplied by 1.2, raised to the power of n minus 1. Ask the calculator to solve for n. Alright, this is where we have to be a little careful. The question asked us the first week during which he runs more than 42 kilometers. So, looking at this right here, on the 15th week, he runs exactly 42 kilometers. But we imagine that it's only complete weeks that we're dealing with. So if we ask ourselves about the 15th week he hasn't yet run 42 kilometers. It's somewhere in between the 15th and the 16th week. It's not until the 16th week that Devi actually runs 42 kilometers. So going back to the document, we would write 16th week. So n is equal to, first we'll put the decimal place, 14.47. But really, if we want the first week during which Debbie runs more than 42 kilometers, it wouldn't be until the 16th week. 15th week he hasn't yet. 16th, now he's exceeded. He's run more than 42 kilometers. Okay. Part E. Find the first week that the total distance that Debbie has run since the start of training exceeds 150 kilometers. Okay, so nice question. What are they asking us here, and what kind of tools could we use? This is a sum, once again, a sum of a geometric sequence. And then we want to find, similar to what we did in this first part right here, what is the first week where he has a total distance of more than 150 kilometers. So total distance sum of a geometric sequence, when does it exceed 150 kilometers? So let's go ahead and work that out. I'm going to put a divider here, and then we'll find E. Okay. Geometric sequence formula in the formula booklet. Here we are right here. Sum of n terms of a geometric sequence. Again, two formulas. Here it doesn't matter as much as it did with the arithmetic sequence. What the difference is right here is just what's in the denominator. We either have r minus 1 or 1 minus r. They're the exact same formula. This is just the idea that if r is greater or less than 1, then we don't have to deal with negatives in the denominator. So let's say if r is like 2, we have 2 minus 1, there's no negatives in the denominator. And we say, okay, let's use this, it's a little cleaner. Or if r is 2, once again, we have 1 minus 2, which gives us a negative in the denominator. And maybe it's less clean, I suppose, in some kind of way. It doesn't really matter so much, because by and large we'll put this into the calculator. I think this is standard as any other. So let's just go with this first value. So to clean this up a little and just talk about these variables, just really quick. This is value of the first term, r common ratio, term number, and then r once again, common ratio. All right. So here we are. Sn is equal to u1 multiplied by r raised to the power of n minus 1 over r minus 1. Okay, so u1, how far did Devi run in the first week, is 3. And common ratio is 1.2. So he runs 1.2 times as much as he did in the previous week. N, term number, we leave that blank. This is the unknown we're trying to solve for. Minus 1 over common ratio 1.2 minus 1. And we're good. We want to find the time or the week in which he runs total distance of more than 150 kilometers. So we can say 150 here. Here we're actually saying when does n equal to 150? I guess maybe more proper in some ways. We want to say what is the value of n for which this business, the amount that Devi runs, the total amount that he runs, exceeds, is greater than 150. On an actual IB exam, it wouldn't matter if you were to write equals or greater. This is more proper notation in some ways. When does total distance run? When is it greater than 150? When we work this out using nsolver graphically, we're going to need to replace it with an inequality. So I guess just keep that in mind. So let's go to the calculator and work this out. So menu, algebra, numerical solve, total distance of 150, and then let's set this up. So 3 times, open up a bracket here, 1.2 raised to the power of n minus 1 over 1.2 minus 1. Here we're asking the calculator to solve for n. So in the 13th week, or just after the 13th week, he runs a total distance of 150. Similar logic to the previous question, it's not until the 14th week that he runs a total distance, or that the total distance that he runs exceeds 150 kilometers. So in this case, we'll write 14 as our answer, the 14th week. Going back to the document here, n is equal to 13.152. In this case, it is not until the 14th week that he runs more than 150 kilometers in total. Okay. Not a bad first question. Part 2. Aidan works for Woodcraft Wonders, a company that makes wooden letters. He wants to predict the demand for different letters. He thinks that letters earlier in the alphabet are more popular. Aidan finds that, in the year he was born, his name was the most popular in the United States. From the 10 most popular boys' names, his name was first alphabetically. This data is shown in the following table. So here we have the popularity, the 10 most popular names for when Aidan was born, and then, looking at the first letter of each name, the position in the alphabet. Okay. Aidan calculates the Spearman's rank correlation coefficient, RS, for this data. Find RS and use the following table to interpret its value. Okay, so kind of actually two questions wrapped up into one. First, we want to find RS, and then we want to state the strength of this significance. So is it very weak or is it a very strong relationship? So let's first find Spearman's correlation. In this case, actually, it's kind of interesting. Usually for Spearman's questions, we actually have to rank, as in we rank the popularity from 1, 2, 3, and so on. And the position we would rank as well. But here we actually already have the ranks. This is rank in popularity, and this is rank in terms of its position in the alphabet. So we can actually go ahead and input this into our spreadsheets, and then run Pearson correlation. Running Pearson correlation on ranked data gives us Spearman. So it's already in the form that we need. Put in the spreadsheet, find correlation, and then we've got Spearman. So let's go ahead and do that. So here we are, spreadsheets. Label these X and Y, and then we'll put our values. So this is 1, 2, 3, 4, 6, 7, 8, 9, 10. And then we'll put the corresponding position in the alphabet. 6, 7, 2, 9, 5, 4, 8, 10. Okay. I'm going to check that everything is entered correctly. 5, 4, 8, 10. Okay. So now let's run two variable statistics. We're comparing popularity and position. So menu, statistics, stack calculations, two variable statistics. Went away. Try again. Okay. I think it could be that I'm within this Y. I'm not sure. I'm going to try it once more. Sometimes it can be a little finicky. There we go. X was in the X, Y is within the Y. This is all okay. Let's go down and find R. Here we go. So R, which is usually Spearman, in this case R is 0.648485. Since we already have ranked data, running Spearman correlation or running linear correlation on ranked data gives us Spearman. So this is our Spearman correlation, 0.648485. So let's write that out. Here we are. RS is equal to 0.648485. To 3 6 figs, this would be 0.648. Okay. Let's remember there's a second part of this question wrapped up with this. Use the following table to interpret its value. So 0.648 is between, well, 0.6 and 0.799. So it would be a strong relationship. Since this is a 4-mark question, I think it would be a good idea to, I guess, instead of just writing strong, to write, for example, there is a strong monotonic relationship or a strong positive relationship between the ranks. So mentioning ranks, just to highlight that we're running Spearman here, just because it's 4 marks question. So let's go ahead and do that. So what do we have? We have a strong positive correlation. And then to show, or just to emphasize that we're running Spearmans here, correlation between the ranks, And if you wanted to, you could talk about the variables as well. Strong positive correlation between the ranks of, in this case, popularity of names and position in alphabet. But hitting these keywords, strong, and then rank, strong positive correlation between ranks is going to be enough. Okay. Question 2 continued. Woodcraft Wonders makes the letter N from a wooden rectangular prism with a depth of 4 centimeters. The front surface is a rectangle with a base length of 13 centimeters and a height of 14 centimeters. 2 identical right-angled triangular prisms are then cut out of the rectangular prism to make the letter N as shown in the diagram. Part B asks us to find the area of the front surface of the letter N. So this shaded area right here. So I would say this, reading an IB question, the IB doesn't often give irrelevant information or information that's just for like trivia. Oftentimes everything is kind of purposeful. So they're telling us that these 2 identical right-angled triangular prisms are cut out of this rectangular face. And that gives us a hint of how we can solve for the area of this front surface right here. So if we have this rectangular surface, we're dealing with positive space. Then we have this negative space, which we want to, I suppose, cut out. So I want to write an equation for this. So if we're talking about the area shaded, which I guess I'll call this AS. So area shaded. Area shaded is equal to what? Well, the area of this whole rectangle, we can either call this AT or AR, the area total or area rectangle. Let's call it AR. So the area of the rectangle minus area of the rectangle minus these 2 triangles. So 2 triangular faces. So let's say AT. This would be an equation for the shaded area. So shaded area is equal to total area minus these 2 identical right triangular faces right here. Okay, so remember they are identical. Okay, so first off, let's find these values. What is the area of the rectangle? This larger piece. What's a 13 by 14 rectangle? So we can write that out. It's equal to, this is a 13 by 14 rectangle. Okay. And then what about these triangular faces? We have 2 identical triangular faces. Okay. So this side length is 13. Rectangles have equal and opposite side length, so equal opposite side length. This is 13 from one end to the other. This is 4, this is 4. What must this missing piece be if we're to make a total distance of 13 once again? 4 and 4 is 8. 8 plus what is equal to 13? 8 plus, in this case, we would have 8 plus 5. 8 plus 5 is equal to 13. Adding this up as well, 4, 5 is 9. 9 plus 4 is 13. It's the same as well. Okay. So I'm going to write this. Area of a triangle, remember, is 1/2 base times height. Or we could say base times height divided by 2. So we know what the base is. And the height is 7 since they're identical. So this is right here is 7. So we know what the area of this triangular face would be. So 2 is equal to, and then we have base times height divided by 2. Okay. So we now have the area of this shaded region. Area of the rectangle minus 2 times the area of these triangular faces. So let's go into the calculator and work that out. So 13 times 14 minus 2 times, I'm going to open up a fraction, base times height divided by 2. And that's bad. Okay, so why is that bad? Well, because we have negative area. So it's possible that I entered something incorrectly, and I guess you can see as well, it's this plus sign where it should be multiplied. So once again, area of the shaded rectangle, so area of the rectangle is 13 by 14. So of course it should be multiplied minus 2 times rectangular faces. Okay, 147 looks better. Okay, so going back to the document here, 147. Good. Let's include our units, centimeters squared. Okay. Part C, calculate the volume of the finished letter N. So only a 1-mark question. Volume, we know the area of this front surface right here, and we know it is extended, or we have an extension of 4 centimeters. So if we want to find the total amount of space that this letter N takes up, or its volume, it would be what we often say is area of the base times height, or area of uniform cross-section times extension. So in this case, area of the face is 147, multiplied by 4 would give us our volume. So let's write that out. Volume is equal to area uniform cross-section times extension of 4. So 147 times 4 gives us 588. And our units are centimeters cubed. Okay. Woodcraft Wonders has 2 machines that make the wooden letters, Machine A and Machine B. Aiden wants to test if the machines are producing letters of different weights. A sample of wooden letters in the shape of an N are taken from both machines and weighed. Okay, so here's Machine A. These are the samples of the letters N, I suppose, that they're making, and Machine B, the weight of the N's that Machine B is making. Aiden assumes the samples came from normally distributed populations with equal variances, and he performs a t-test at the 5% significance level. So I guess maybe one thing to keep in mind, normally distributed with equal variances, sometimes they ask you for these questions, they say, what is Aiden assuming in order to run a t-test? Well, he's assuming that we have normally distributed populations with equal variances. Sometimes they'll give it to you, but sometimes, very common actually, first question is, what is the assumption that Aiden is making? Well, he's assuming they're normally distributed populations, that they have equal variances. Okay. Part 1 of D, write down the null and alternative hypotheses. Okay. So a t-test compares means, that is to say the average, in this case the average weight of these N's that are being produced. We can write the mean as mu. So mu, let's call this mu A, the average from machine A, and the average from machine B. T-test compares means. So what could we possibly have here? I'll write this out right here, I guess. So null hypothesis, null is this 0 right here. Null is like the German null, 0, status quo, no difference. So in this case, status quo, no difference, mean A, average from machine A is equal to the average from machine B. Null hypothesis, status quo, no difference. Alternative hypothesis. What is our alternative hypothesis? In this case, we have a few options when we're dealing with a t-test. Maybe I'll write that. I can write that here. We either have, I'm going to try to do something, hopefully not too fancy. We have a few situations that could potentially be the case. We can either have mean A and mean B, average of machine A and average of machine B are just different. They're different means. Could be that mean A is bigger, or it could be that mean A is smaller. To find out what exactly, in this case, Aiden is testing for, we just have to read the question. So, normally distributed populations. Let's see what he wants to find out. Aiden wants to test if the machines are producing letters of different weights. So in this case, he doesn't want to find out if A is producing bigger or smaller. He just wants to see if the machines are producing different weights. So in this case, we're going to deal with this right here. Mean A is not equal to mean B. That's the alternative hypothesis. All right. So not the others. This is important because we're going to need to put this data in. We're going to need to put the alternative hypothesis when we run a t-test. Okay, so let's do part 2 right now. Find the p-value for this test. Okay. For that, we'll need to go into the calculator, and we'll go into spreadsheets and work that out. So here we are. Set up a column of A and B, and then we'll put the values in for each. So this is machine A first. 42, 361, 343, and so on. 364, and I'm going to put the others in right here. 343, 332, 358, and so on. Alright, I'm actually just going to check these really quick. 243, 28, 76, good. Good. Alright, let's run a t-test here. So menu, statistics, stat tests, and we want to do 2 sample t-tests. He took a sample from machine A and from machine B. So list 1 was in A, list 2 was in B. Null hypothesis is already set. This is correct. mu1 does not equal mu2. And then pooled, we always, in AISL, always say pooled is yes. This is that equal variances and normally distributed populations. So pooled is equal to yes. All right, here's our p-value, 0.1019. So going back to the document, we'll write this out. So this is part 2. P-value is equal to 0.1019, or I guess we could say 0.102. All right. Part 3, write down the conclusion of the test, give a reason for your answer. Okay. So, actually just use the space down here. So conclusion of your test. For this, we can pair p-value and p-crit, or the significance level. Our p-value that we found was 0.102. Since our significance level is always as a percentage, I'm going to actually convert this to a percent as well. So multiply by 100, or just move the decimal place over 2. This is 10.2%. And our significance level itself was 5%. So what do we know? We know our p-value is greater than the significance level. So in this case, we would We accept the null hypothesis, or more properly, we say we fail to reject the null hypothesis. There's not enough evidence for us to reject the null hypothesis. So just to provide a little context of what this p-value actually measures, p-value measures the probability that we see these kind of results just based on sampling alone. So we take some letters from A, some letters from B, we compare their means. Yeah, sure, they're a little different, but how different are they? We're going to see these results, well, 10.2% of the time. So particularly likely, but it's not enough for us to say with more conviction that there actually is a difference. Our cutoff point is 5%. If it's less than like 5% likely that we're going to see these results, then that's a little unusual, and it leads us to believe that there actually is a difference. Here, our p-value is 10.2%. Not super convincing. It suggests that, well, maybe, but our cutoff point in this case is 5%. So we assume that mu1 is equal to mu b. There is insufficient evidence to reject the null hypothesis. So this is what we could say. There is insufficient evidence to reject HO. We wouldn't exactly want to say accept the null hypothesis, but we can say that there's insufficient evidence to reject it. So outside of convincing argument, we are not left in limbo or kind of like inconclusive state, but we can't rule out the possibility that they aren't actually just the same. All right. P-value greater than p-crit, accept the null hypothesis, phrased in a little more proper terminology. We cannot reject it. We can't reject. We cannot reject it. Insufficient evidence to reject the null hypothesis. Question 3. Enola has a triangular-shaped farm with boundaries of length 1,600 meters, 1,500 meters, and 1,400 meters. Part A asks us to find the area of the farm. Give your answer in the form a times 10 to the k, where a is greater than or equal to 1, less than 10, and k is an element of the integers. So this z right here stands for the German Zahlen, or counting, and it is positive, negative whole numbers. So no fractions, no decimals, just 1, 2, 3, 4, 5, 6, so on, and the negatives potentially. This right here is scientific notation. This is some value. It could be a decimal potentially. It could be like 3.63, something like that. And this is times 10 raised to the power of k, where k is again 1, 2, 3, 4, 5, and so on. So essentially they're asking us to find the area of the farm. Whatever the value is, we want to write it out in scientific notation. Okay, so sometimes these questions can be intimidating where there's one large question with little scaffolding and just a fairly significant number of marks. But I think it's often helpful, especially during that 5-minute reading time, to, I guess, not exactly compartmentalize, but to narrow down the focus of the question, to see what the question is asking you, what kind of, I guess, syllabus strand it's in, what the domain is, and then work from there. So first thing we could ask, we want to find the area of the farm. We have a non-right angle trigonometry question, and we can say, okay, well, know how to find the area of a non-right angle triangle. And we could look into our formula booklet. I'll write this out really quickly. A is half AB sine C. This is our area of a non-right angle triangle, where if we have two side lengths and an included angle, that is to say an angle between those two side lengths, we can solve for the area. But we might say, oh no, we don't have that. We don't have any angles at all. And say, okay, well, we're still in the realm of non-right angle trigonometry. We know we can apply this area of a triangle rule if we have two side lengths and an included angle, but we don't yet have any angles. So how can we find an angle? And then within our non-right angle trigonometry, we have sine rule and cosine rule. Sine rule, remember, pairs up angle opposite side length, angle opposite side length. And if we have 3 out of those 4 unknowns, that is to say a side length, and an angle, side length, and an angle, if we have 3 out of 4 of those things, then we can create an equation and solve for an unknown. Sine rule is the easiest one, but we don't have those things in this case. And the other option is the cosine rule, which compares 3 side lengths and an angle. And if we have, once again, 3 out of 4 of those things, then we can solve for the unknown. And in this case, we do. We have 3 side lengths. We don't have the angle, but we have enough information. We know 3 out of those 4 things that we can use the cosine rule. So let's go ahead and do that. It's kind of arbitrary which angle we want to solve for. I guess my mind kind of just draws towards this one. And really, we could choose any, though. Okay. So strategy is we're going to use the area formula to find the area of this farm, but we need an angle. We need this included angle. So let's find the angle between these 2 side lengths, and then we should be good. So let's use the cosine law. Let's go into the formula booklet to find the cosine law here. So we'll go into geometry and trigonometry, and we'll find the cosine formula. So here we are. We have 2 different versions of the cosine formula. Just like the arithmetic sequence formula that we saw earlier, they are the exact same thing. They're just rearrangements. So they're 2 expressions of the same formula. So which one could we use? Again, since by and large, I think many of you are probably using nsolve to solve for this, it's kind of arbitrary. This one over here to the right has as the subject, or the value that's all by itself, the angle, whereas this one has a side length all by itself. So more properly speaking, if you wanted to solve an unknown angle question, you would use this one because the angle is already by itself. And if you wanted to find a side length, by and large, you would use this one because the side length's already by itself. Since we're going to use nsolve, it doesn't actually really matter. And I sometimes recommend this one just because I think the form is a little cleaner and it helps us with this pairing of side length and an angle, which is the one thing we have to be mindful of when we use the cosine rule. So I'm actually going to use this one on the left. So let's go ahead and write that out. Okay. So here's our cosine rule. It's a squared equals b squared plus c squared, which is a lot like the Pythagorean theorem actually. And then we have this modification, minus 2bc cos, and then I'm going to put a capital A. So we see a, b, c. B and c occur once. There's a small bc as well. But we see a actually occurs twice. So I want to just draw attention to that. So a occurs twice. And why is that? So if we look at the labeling of a triangle, I'm just going to draw this really quick. Angles are often or are always given in uppercase, and then side lengths are given lowercase. And when we label our triangle, we pair angle, opposite side length, angle, opposite side length. So when we see this a appear twice, this small a refers to the side length, and this large a refers to the angle that is opposite. So we just have to be careful when we substitute. We need to make sure that these two correspond to each other. That is to say, the side length is opposite to this angle is opposite to this side length. Okay, and I think I'm going to leave it at that. I guess I would say one last thing. Why is that? Well, because just like, I guess, the crocodile's mouth in a way, if we imagine some angle right here, and then the potential side length that is opposite, if the angle opens larger, we have, well, a larger side length, and so on and so on and so on. We can imagine opening up larger, and then a larger side length that is opposite to it. So essentially, why do we have this pairing? Well, because the length of the side length that is opposite to the angle, they're proportional or related to one another. A smaller angle leads to a smaller side length. A larger angle leads to a larger side length. That's why we pair them together. Okay, let's go ahead and substitute into this equation here, and I think we should be good. Okay, so a squared A squared we want to keep opposite to the angle that we want to find. So for a squared, we're going to write 1400. So 1400 squared equals, and then b squared plus c squared. 1500 squared plus 1600 squared minus 2 times 1500 times 1600. And then cos, we don't actually know what this theta is, but it's opposite to this a that we selected, cos theta. Okay. So now we have one equation and one unknown, just this theta. Let's go ahead and solve and find this unknown. So here we are. Menu, algebra, numerical solve. And then we can write out our equation here. 1400 squared, 1500 squared, plus 1600 squared. Then minus 2bc. And then we have cos a. Cos, and then we can write cos theta, cos a, we're going to write cos a. Okay, and we ask the calculator to solve for a. Make sure you're in degrees. And I think we're good here. So the angle is 53.5764. So let's go back to the document and write that out. So theta is equal to 53.5764. I'm going to keep all of the digits here because we actually want to use this theta value to find the area. If we round to 3 sig figs, it could potentially make a difference. We only really want to round to 3 sig figs once we get to the end of a question. So we're still in the middle of the question. We still want to use this value to, in this case, find the area. So we want to maintain as much accuracy as we can. So we keep all of our digits for now. Okay, so let's find the area of the farm. And for this, we'll use our area formula for a non-right angle triangle. So half AB sine C. Okay, so I'm going to erase this triangle here, and then we can just use this space. Okay, so half AB sine C. So actually, maybe I'll bring this up just for a sec. What is half AB sine C referring to? It refers to two side lengths. In this case, we could write A and B, and then an included angle. So the angle in between. So we say the two legs of the triangle, and then we need the angle in between. And when we have that situation, or that combination, then we can solve for the area. Okay. So half, we know this theta value here. We know that it's 53.5764. So A would be 1500. B would be 1600. And then we have sine. And then we can keep the full digits here. 53.5764. All right. So once again, two side lengths and the angle in between. All right, let's go ahead and solve this on the calculator. So here we are. Open up the fraction. So 1/2 A, B, then we have sine C. You can actually copy paste these and keep the whole digits, the whole number of digits that you have. That's always an option. I don't think there are a few cases where you need that many digits, that level of accuracy. So I'm just going to keep to what we had, the 53.5764. All right, we're in degrees. Let's go. Okay. So we have 965,579. This would be square meters. Okay, so let's go ahead and write this out. So 965,579, and this is meters squared. Since we want to round this, or put this into scientific notation, our final answer will be in 3 sig figs. So I'm going to round this to 3 significant figures. So 966,000, and then this would be meters squared. Okay, so last step right here, we want to put this into scientific notation where we just have some digit in the front and then we multiply it by 10 to the power of something. So I think the easiest way to, work this out, this a that we want right here has to be between 1 and 10. It has to be less than 10, but greater than or equal to 1. Okay, so essentially we want a value right here. Well, we just want the ones column essentially. So anything from 1 all the way to 9.99999. So we want to deal with the ones column. What essentially we want to do is we want to bring the decimal place so that it stands where we just have the ones column and then some decimals behind it. So how can we do that? And how can we relate that to this 10 to the power of k? A nice kind of trick is, here's where our decimal place is right now. Let's count the number of hops, or how many times we would need to multiply by 10 to get a certain value that we could write in scientific notation. So here we go. 1, 2, 3, 4, 5. If we wanted to move our decimal place over here, we would have to go 5 hops. Now we can write out 9.66 times 10 to the 5, number of hops that we meant. So how does this work? This is 9.66 times 10 to the 5, or I guess this would be 9.66 times 100,000. And that's how we could write out scientific notation. I think it's always helpful. So start at the end, count the number of hops. That's how many times you would need to multiply by 10 if you were to get 9.66 times, well, in this case, 10 to the 5. And that's it. Enola's farm has a barn and a farmhouse. Enola is constructing a 2-meter wide straight path on the level ground between the barn and the farmhouse. The barn is located 300 meters east and 200 meters north of the farmhouse. Part B asks us to find the distance from the barn to the farmhouse. Okay, so the first time I read this question, I wasn't entirely sure how to visualize what was going on, particularly because they were talking about a farm, a barn and a farmhouse, and a farm. So the farm contains the barn and the farmhouse. So if this is the farm right here, these are the bounds of the farm. We have a barn and a farmhouse which sits on the farm. So we might imagine, for example, we have the barn, if I can get this to go. We might have the barn and then the farmhouse right here. And they tell us that the barn is located 300 meters east and 200 meters north of the farmhouse, which actually means that I should switch these around. Just to visualize this, what would we have? We would have the barn located 300 meters east and then 200 meters north. I know this isn't entirely to scale, but just to visualize, 300 meters east, 200 meters north. And this is the situation that we have here. And they're asking us to find the distance from the barn to the farmhouse. So since we are actually just dealing with what are called cardinal directions, that is to say we go straight east and straight north, what happens is we create a right angle triangle, and now we have a situation where we can use Pythagorean theorem to solve for some unknown side length, this one right here. So let's go ahead and work that out. I'm going to draw a little divider here. So Pythagorean theorem, once again, a squared equals b squared plus c squared. Two side lengths that we have, 300 and 200. So we have 200 squared plus 300 squared should equal a squared, or this side length squared. We've got an equation with one unknown. We can actually go ahead and end solve this. We could work it out using algebra as well, but let's skip right to end solve. I think that should be fine as well. So menu, algebra, numerical solve. a squared equals 200 squared plus 300 squared. That's calculator to solve. So the distance is 360.555. Let's write that out. 360.555. Three significant figures. This is 361, and then the units are meters. Okay. So 361 meters. 2-mark question. So show the equation and then the answer. All right. The path costs $120 per square meter. Find the cost C of the path to the nearest dollar. Okay, kind of interesting question. First, here they asked us to find the distance from the barn to the farmhouse. So just this absolute kind of walking distance, the length in some ways. Here they're asking us to find the area. So, or I guess the total amount that it costs to, what could we say? To make this path. So knowing that the path itself is 2 meters wide, that we have the length, and it costs $120 per square meter, how much would the path cost? So if I can just, I'm going to try to do this. I hope this isn't too fancy or anything. But if we imagine, for example, that this is a section of our path, what does that look like? So we have some element of the path. Here we go. And if this is just a section of the path, it also has a thickness. It has a thickness of 2 meters. So 2 meters. We know its length. Its length is 361, and across that 361 meter length, it has a width of 2 meters. So essentially what we have is a rectangular surface. So let's move this down here, kind of running out of space in some ways, but I think we should be okay. So this is 361, this is 2, and now we need to find essentially the area of this rectangle. Area of a rectangle is length times width. So we would have area equals 361 times 2, which would just give us, this would give us 722. 722 meters squared. Okay, this is the area of this total path. But what is the cost if the path costs $120 per, or for every square meter? 722 square meters cost $120 for every square meter that we have. So what we can say is 722 multiplied by 120, and this should give us our total cost for this path. So I'm going to work that out on the calculator here. We have 722 times 120. Total cost of this path is $86,640. Okay, so let's write that out. So $86,640. Okay. Good. I'd say, for a 2-mark question, it's on the lower bound of how much work is required, but maybe that's fair. Okay. Enola takes out a loan to pay for supplies to make the path. Enola borrows C dollars for 5 years, compounded monthly. To repay the loan, she makes a payment of $1,750 at the end of each month. Part 1 of D asks us to find the total amount of interest paid, and Part 2 asks us to find the nominal annual interest rate of the loan. Okay, so interesting question. It strongly suggests that we're going to need to use financial mathematics and likely the financial solver. So anytime you have these repeated payments through time are situations where we need to use the financial solver. So no longer even the compound interest formula, we're going to need to use the financial solver. But what about this first question, the total amount of interest paid? I wrote down earlier each of the parameters for the financial solver, And if we look through them, we have total number of payments, interest rate, present value, payments made, or incremental payments made each month in this case, final value, and so on. But there's nothing that allows us to directly find the total amount of interest that is paid on a loan. So this question, we actually don't need the financial solver yet. This first part 1, is more of a conceptual question. So if I can walk through this certain situation and try to unpack what's going on and how this might link to the total amount of interest paid. So Enola goes to the bank and she borrows $86,640. This is the initial amount that she borrows. And we know how much she pays back to the bank. She pays $1,750 at the end of each month for a total of 5 years. So with that, we can find out the total amount that she gives back to the bank before this loan is paid off. And we also know how much she took out. And these two, generally speaking, almost always, unless the interest rate is 0, these two will not match. We'll find out that she's paid back more than she actually borrowed in the first place. And that additional amount that she has paid back is interest that the bank charges for the privilege to take out money. It's the fee that the bank charges to borrow money. So if we can write this out, interest paid, the interest paid, total amount of interest paid, would be equal to, well, the total amount paid. So the total amount that we pay minus initial amount, the initial amount that we borrowed. And we'll see that these two aren't the same. The amount that you pay back, so we should say total amount paid. The total amount that you pay back will be larger than the initial amount that you borrowed. So let's find these values out. So how much did she pay back to the bank? Well, over 5 years, she had made monthly payments and she paid $1,750 each month. So $1,750 times 12. So every year she made 12 of these payments. And she did this for 5 years. That's the total amount that she paid back. And the initial amount that she borrowed was $86,640 to build this path. And we'll see when we work these out that these aren't the same, that she actually paid back a little more than she borrowed. And that extra amount that she paid back is the interest that she provided to the bank. So let's go to the calculator and find the difference between these values. So 1750 times 12 times 5 minus 86640. All right, so $18,360. So writing that out, we have $18,360. Okay, so this would be the total amount of interest paid on the loan. Once again, she went to the bank, she took out $86,640. She ended up paying significantly more than that. What's the difference? Well, the difference is in interest that she paid to the bank. Okay. Part 2, find the nominal annual interest rate of the loan. Okay, so what is the interest rate? She's paying off some interest, but what is the actual rate that the bank is charging her? For this, we'll need to use the financial solver, and we'll need these parameters right here. So let's go into part 2 right here. And I actually think I'm going to grab some of this and bring it up, just so we can see the values in the question itself. Okay. So let's go ahead and try to find these unknowns, and then we can solve this in our financial solver. So first off, we want to find nominal annual interest rate. So let's highlight that right here. Present value of the loan $86,640. Remember, we usually say money flowing out, money flowing in, determining positive and negative. In this case, since she's taking out a loan, this is actually money coming towards her. This is money that she has in her possession. So it's coming towards her, money that's available for her to use. This would be positive, $86,640. PMT, payments, $1,750. This is money flowing out, so we put a negative here. So it's leaving her pocket and going to the bank. Final value of the loan is 0. She's going to pay it off. Payments per year at the end of each month. Compounding periods per year. It is compounded monthly. All right, last one is N. So total number of payments. Total number of payments is linked to PPY. In this case, 12 payments per year over 5 years. This is a total of 60 payments. So total number of payments made is 60. Looks like we have everything we need. So we just have one unknown for interest. We can go ahead and solve this. So let's go into the calculator and work this out. Menu, finance, financial solver. We can do this as well, 12 times 5. I always kind of like that trick. Whoops, let me do that again. 12 times 5, and then we can just go into another column. All right. Present value, negative 1750. Final value is 0. And then both of these at the bottom are 12. And then she pays at the end of each month. All right, everything looks good. Let's go ahead and solve. 7.837% interest rate. Okay, so let's go back to the document here. And we can write that out. So here we have 7.837%, or to 3 significant figures, 7.84%. Okay, good. Question 4. A particular island is only accessible by road at times when the water level is low enough. Otherwise, the road is underwater. The height of the water above the road, h meters, can be modeled by h of t equals a sine bt plus d, where t is the time measured in hours from midnight on Tuesday. The first maximum high tide is at 3:36 with a height of 1.26 meters, and the first minimum, the low tide, occurs at 10:48 with a height of negative 0.26 meters. This is shown on the graph. Okay. Part A asks us to find the value of a, given that a is greater than 0. And then just looking down further in this question, we have find the value of d, find the period of the function, and then find the equation. Questions like this often unfold in this similar way, where we're asked to find the parameters to complete a trig function, that is to say the a, the b, and the d. So asking to find the parameters of some equation, and then using that equation to do something practical in context. So this is how these often unfold. And trig function questions are not too uncommon, actually. I think they're actually fairly common. So I think these are one of the ones to have in your back pocket in some ways. And the structure is often quite similar as well. Okay, so let's work this out. Find the value of a, given that a is greater than 0. So I think it's often helpful to actually label these points that they give us first. So I'm going to go ahead and start with that. So a is at 3:36 with a height of 1.26 meters. So what's going to be interesting is, and what makes this, I think, a more challenging question, is that we can't put in 3:36. That's not a coordinate point that we're going to be able to. We're going to need to write some decimal value. So it's going to be 3 point what, essentially? Well, we have 3 plus 36 out of 60 minutes, if we wanted to write this as a coordinate point. So going to the calculator here, we have 3 3 hours plus, well, what do we have? We don't have a full hour after that. We have 36 over 60. We have 3/5 of an hour. I think it's going to be helpful if we write this as a decimal. So converting this to decimal, 0.6. So we have 3.6. So after 3.6 hours, the height is 1.26 meters. And then we have the first minimum, which occurs at 10:48, and it has a height of negative 0.26. So 10 hours plus 48 minutes out of 60. Let's go to the calculator and work that out. So 48 out of 60, 48 is divisible by 12. So it should give us a nice number as well. 4/5 is 0.8, which we could find out as a decimal as well. So 10 hours plus 48 over 60, or 4/5 of an hour, or 8/10, 10.8. So after 10.8 hours have elapsed, the height is now negative 0.26. Okay. So this essentially, working with time, we have to be careful about what are our inputs, essentially. Okay, let's go on and try to find the value of A right here. So A refers to the amplitude. Essentially, I'm going to draw a line here. So if we draw this midline right here, this value of A refers to the height of the wave. So distance from the max to the midline, that would be A, or from the min to the midline, this would also be A. There are certain formulas that we can use. They aren't in the formula booklet, but I think they're helpful to remember. A itself is equal to max minus min over 2. So remembering conceptually that A, the amplitude, is the height of the wave from the midline. If we take the total height to the total, I guess the minimum, from the highest point to the lowest point, we would have, well, 2 complete waves. So take that total distance, divide by 2, and it gives us the height of one wave, essentially. All right, so let's substitute and work that out. Maximum height is 1.26 minus, careful, the minimum is already as a negative 0.26. So minus 0.26. 2 negatives make a positive. Essentially, we're going from 1.26 and then adding another 1.26. That's going to give us the total distance. We want to divide this by 2 again. So we can put this into the calculator. I'm going to work this out. 1.26 plus 2.6 would give us 1.52 over 2, which we can write as 0.76. Okay, there it is. So A is equal to 0.76. So if I can write that out, A is equal to 0.76. In part B, we're asked to find the value of D. So D is the parameter right here within our trigonometric function, and it refers to either the height of the midline, essentially the y value of our midline, or the phase shift. So essentially, if we remember, our normal sine and cosine function are centered about this line y equals 0. But that's not useful for us in all cases. There are cases where we might want to shift a function up or down, and then of course this value is then the value of D. Another way to look at this was originally y is equal to 0. That was previously the midline of our trig function. And now in this case, if we shifted it up, this would be the value. So they refer to the same thing. How much are we moving our function up or down by? Or another way to say it, what is the value of this midline? This is y is equal to d. Okay, a few different ways we can solve this. There is another formula that we can use, and once again, it's not in the formula booklet, but it's helpful to kind of have in memory. So value of d is equal to max plus min over 2. So if we think of the midline as, in some sense, the average, where the highs and the lows are cancelled out, or the resting line, what we can do is we can take the max, we can take the min, divide by 2, average it out, and then it'll give us this midline. So let's do that again. So we have 1.26 plus, in this case, but then watching the negatives once again, 0.26, negative 0.26. divided by 2, this should be a nice number. This is just going to be 1 over 2, or as a decimal, we could write this as 0.5. All right. D is equal to 0.5. Okay. Find the period of the function in hours. Okay, interesting question. So period of the function in hours. So period refers to the time taken to complete one up-down cycle, or one complete wave. So if this is our starting point, how long does it take to get back to this starting point? Same way we could take what's called the peak. How long does it take to complete one complete cycle? Or the trough. How long does it take to complete one complete cycle again? Okay, so period, how long does it take to complete a full wave? Let's look at this. Here we have our first maximum at 1.26 hours, and then our first minimum at 10.8 hours. So how much time has elapsed for us to go from the max to the min? We can find that out. That would be 10.8 minus 3.6, and that would be 7.2 hours. Okay, so it took 7.2 hours to go from the max to the min. But that's only half a cycle. It's not a complete cycle. Since we have symmetry here, 7.2 hours to go from the max to the min, another 7.2 to go from the min to the max. So if we want to find the total time taken for one cycle, we could take 7.2 and multiply it by 2. So 7.2 times 2 would give us 14.4 hours. All right. In part D, we're asked to find the equation of the model. Okay, so let's first look at the equation once again. Here it is, h of t equals a sine bt plus d. We found a right here, the amplitude, and we found d explicitly right here as 0.5. And they even gave us these parameters. In part C, they asked us to find the period, and we did, but it's important to note, and these things are sometimes confused, B itself isn't exactly the period. It's related to the period, but it's not the period itself. B, more properly speaking, is actually called the frequency, referring to the number of up-down cycles in 360 units. And why that is has to do with something called the unit circle, and it's a little more, I guess, depth than we really need for this question. But what is important to know is that B itself is not the period, but we can find this value of B using the period. So once again, we have an equation to draw on. It's not in the formula booklet, but in order to solve these kind of trig questions, we kind of need to remember this or have this in the back pocket in some ways. Okay, so what is the value of B? B is equal to 360 divided by period. So once again, kind of mentioned, B refers to the frequency, how many complete waves you can fit within 360. Our period itself was 14.4. So taking 360 divided by 14.4 would tell us how many waves we can fit into 360 units, in this case 360 hours. And again, it's a little more depth than we need for AISL. I wouldn't say AISL, but I'd say for this question. It has to do with the unit circle and the idea that we sweep through one full rotation in 360 degrees. And I think that's all. I'll get into it for there. So let's find the value of b here. 360 divided by 14.4. So 360 divided by 14.4 is 25. It's a nice number. Okay. 25 is the value of b. So now we have everything we need for this function. I'm going to write it out and then I'll copy paste and bring it down. H of t equals a sine bt plus d. So we can do it all here, I suppose. So a said was 0.76. Here it is. 0.76 sine bt. B is equal to 25. 25t plus d, which we found here as 0.5. All right. So once again, b is not the value of the period. It refers to the frequency, how many up-down cycles or how many complete waves we can fit into 360 units. 14.4 was our period. That means we can fit 25 waves within 360 units. So total equation of the model, 0.76 sine 25t plus 0.5. Okay. Part E, find the value of h of t at 230. Okay. So we've got an equation, we've got a function which relates height to time. Here, this is essentially an input-output question. They give us a time, and we want to find the height. So we've created some function, now we want to use it to do some practical things. So I'm going to grab this and then work this out here. So this is question E. And we're dealing with h of t. Okay. So first off, what's our input? 230, we're going to have some problems because we have a colon and not a decimal place. If we wanted to convert 230 into a decimal, we have 2 hours plus, well, 30 over 60, or essentially 2.5 hours. So this would be our input. 0.765 sine 25 times 0.5, whoops, sorry, times 2.5, times 2.5 plus 0.5. All right. So input value of t of 2.5 hours. And let's find the height at that point. 0.765. Sorry, it's not 0.765, it's 0.76 sine. I should watch my own writing. So 0.76 sine 25 times 2.5 plus 0.5. Okay. Make sure this is good, this and this. Make sure in degrees. So the height is 1.17413. So writing that out. 1.17413. 1.17 meters to 3 significant figures. Okay. Let's go on. Part F asks us to state the meaning of h of t is less than 0 in context. So h of t is the output. It's the height of the road at a given time. And so this would be the height at a given time is less than 0. So what does this mean in context? They told us initially that this road is only accessible when the water level is low enough, and the height of the water above the road, h, is modeled by this function. So when h of t is above 0, waterline is above the road and it's not accessible. When h of t, the height of the water, is below the road, well, then the water is below the road and the road is accessible. So if we want to state this in context, what does h of t is less than 0 mean in context? We could say that that represents the points where the road is above the water level, or the island is accessible, or h of t is less than 0, we could say the water line is below the road. I think that would be probably what I would choose. So f, what does h of t is less than 0 mean? It means the points where the water line is below the road. Water line is below the road. The equivalent statement would be the road is above the water line, or the island is accessible, and so on and so on. Okay. Part G, we're asked to find the length of time on Tuesday when h of t is less than 0. So essentially, for how much time on Tuesday is the water line below the road? So looking back at our function, I'm going to clear this up just a little. So here is one full day, and it's actually Tuesday, 24 hours. There's a certain amount of time where the water line is below the road. So looking at this, for this amount of time, right here from, let's say, T1 to T2, the water line is below the road. And then also actually moving in from, if we can imagine this is T3, all the way up to 24 hours. There's also this time right here, where the water line is once again below the road. If we can take the total sum of these intervals, so this interval here and this partial interval here, then we can find the total amount of time for which the water line is below the road. Okay, so let's go ahead and do that. How can we do that? I think the easiest way would be to graph it. I think that would be a good visual, and then we can just find these intersection points and then do some subtraction and find the length of these intervals. Okay, so let's go ahead and do that. Let's graph this function. So here's our function once again, 0.76, and we have sine 25. We need to put x because our function is in terms of x. 25x plus 0.5. We have part of this. Let's extend this. We only have 10 hours. Let's put a full 24 hours. So window settings, let's start at maybe -2 and go to 30. The max height, I think of this road, I think 2 should be okay. The max height earlier we saw was 1.26, so that should be okay. And the min height, let's do -0.5. I think that should be actually quite nice. Okay, good. So let's find the zeros. So these points, these intervals right here. So analyze graph, 0. So at 8.84 hours, that's after this point, the water line is briefly below the road, all the way up until 12.754 hours. Find the difference between these two, 12.754 and 8.8456, and we can find the length of this first interval. So let's actually go ahead and do that. So let's go back to the document. I'm going to clear this up and work it out here just because there's a nice visual with this graph already. Okay. So what did we find? We found earlier, I'm going to use these T1, T2, and so. T1 we found was 8.8456. T2 we found was 12.754. We want to find the length of this interval. We'll do T2 minus T1. So T2 minus t1. And what would that look like? 12.754 minus 8.8456. Let's go into the calculator and find the length of this interval. So here we are, 12.754 minus 8.8456. Let's keep all the digits because we're still halfway through a question. Don't round yet. This is 3.9084. Okay. Let's go back to the calculator here. So this is helpful as well. You can cycle through previous windows, not needing to enter the function again. Let's go find the second point. So analyze graph 0, 23.246, and then of course 24 hours. Graph trace, 24 hours where, can't really see it too well, but right here. So if we're just talking about Tuesday, we want to go up to 24 hours. So what's the length of this interval? From 24 all the way to 23.246, so roughly 0.75 or so. Let's go back to the document and write this out for T3. Okay. T3 is equal to 23.246. In terms of this interval right here, it would be T4, which I think is actually maybe easier just to write 24 minus T3. So the 24th hour, 24 minus T3. What's the difference here? So 24 minus 23.246. Working that out really quick. 24 minus 23.246 gives us 0.754. So writing that out. 0.754. Okay. So if we want the total amount of time where the road is above the water line here, it would be adding both of these intervals. So adding this 3.9084 right here, and then also this 0.754 plus 0.754. Okay, so I'm going to add those together. 3.9084 plus 0.754. 4.6624. Okay, going back to the document. 4.6624. Okay. I'm going to see if they're asking us to write this in hours and minutes. Find the length of time on Tuesday. So, total length of time on Tuesday is 4.6624 hours. Okay. Question 5. Tseng models the height of a section of a roller coaster. She uses the following function. So here's a cubic function right here for a domain of x is greater than or equal to 0 and less than or equal to 60, where x is the horizontal distance from the left-hand end of the section and f of x is the vertical height. Distances are measured in meters. Tseng's model is shown on the following graph of y equals fx. So here we have this cubic function, and this is distance from the left-hand side and then height. Point O has coordinates 0, 0, and part 1 of A asks us to write down the definite integral for the exact area between the curve and the x-axis. Okay, so definite integral, remember we're dealing with this sum of a certain amount fx dx. But we have, with our definite integral, what makes it definite is we have a known starting and ending point. So this is our definite integral. This s we can think of as a sum, the sum of the area under the curve of some given function in terms of x. So we have f of x dx. So now what's required of us is finding the starting ending point, and then just substituting this function. Or actually, to be honest, we can actually leave this f of x in here, because this is equals isn't is. This is f of x, this whole long thing. If you want, you can substitute it in, and that's the same thing. Okay, so let's write out this definite integral. We want to find the definite integral for the exact area between the curve and the x-axis. So here we're going from 0 all the way to 60. So we have our starting and ending point. So let's write that out. So going from 0 all the way to 60 of f of x, our function, and then it's in terms of dx. And that's actually all there is to it. So area under the curve is given by our integral. What makes it definite is we know the starting and ending point, and then here's our function. If you feel more comfortable, you can substitute this in, but this is acceptable as well. All right. So there we have A1. Calculate this area. So we'll go ahead and put this into the calculator, but of course we'll put in the value of this function. So let's go and calculate the area under the curve. So here we are, functions, definite integral, starting point of 0, ending point of 60, and let's put that function in 0.1x cubed minus 0.12 x squared plus 4.05x plus 3. And then we've written it in terms of x, so we'll write this in terms of dx. All right, just want to make sure everything is good before we press enter. Looks good. Area under the curve is 2070 square meters. So let's writing that out, or let's write that out. Process could be something like this. So if I can get this, there we are. So here we have our function, and it is equal to 2070 meters squared. Okay, so not a bad question if I guess understand the notation and I guess some of the terminology here and what it refers to. Definite integral, definite because we have beginning and ending points. Area under the curve is given by our integral. So here's our definite integral. And then using that, we can find the area. A light beam from O passes through the local maximum at point M. Part 1 of B asks us to find the coordinates of M. Okay. So this O is the origin. We have this light beam and it passes through this local maximum at M. So we first need to find the coordinates of M. Two different ways we could solve this. One is taking the derivative of this function and then setting the derivative equal to 0 because the derivative gives us a slope at a point. And when the slope is equal to 0, we've reached a maximum. And that we could use to find this maximum point. I think actually a little more straightforward and maybe more efficient is, to be honest, to put this into the graphing calculator and then simply find the maximum. I think that the derivative, this isn't going to be too bad of a derivative as well, but again, I think putting this into the calculator and then just finding the maximum might be a little quicker. So I'm going to go ahead and do that. Or I should say more efficient. So 0.001 x cubed minus 0.12 x squared plus 4.05 x plus 3. Here we are. This looks good. I'm going to zoom out a little. All right. And now let's go menu, analyze graph, and we'll find this local maximum right here. So 24.189. That would be our local maximum. So going back to the document here, find the coordinates of M. I should go back to the calculator just for a sec. So another reason why graphing actually might be more efficient, if we were to take the derivative, we could find the x value, and then we would need to substitute that x value into the original function to find the y value, since they're asking us for a coordinate, that is to say an x, y value, both an x and a y value. So I think graphing is almost certainly going to be the more efficient way for this one. Okay, let's write out the coordinates. So 24.189 and then 44.906. Okay. 3 sig figs, if we want, would be 24.2 and then 44.9. Okay. Part 2 of B, we're asked to find the angle of elevation from O to M. Okay. So we know the coordinates of this point. I'm actually going to copy and bring them up. So these are our coordinates of M. And now we want to find the angle of elevation. So remember, angle of elevation is the angle that we sweep up from the horizon. So starting from the horizon, what is the angle that we need to sweep through in order to, set off and reach some point? So in this case, we want to find this theta value right here. Okay. So how can we do that? They just asked us to find this coordinate point right here. This corresponds to x, this corresponds to y. So what does that mean? So if we start from here to here, we know that this x refers to the horizontal distance we traveled, which was 24.2. And the y value corresponds to the vertical distance that we travel, which is given by 44.9. So now we actually have a right angle triangle, and we can go ahead and use our trig ratios. What side lengths do we have? If this is our angle of reference, our theta, we have the opposite and we have the adjacent. So remembering sa, ka, toa, we have the opposite and the adjacent, we have tan. So we have tan theta, which is a relationship between the opposite and the adjacent. In this case, the opposite is 44.9, this one right here, and the adjacent is this one, 24.2. All right, so now, remember tan is a function, it's not a variable. We have one equation with just one unknown. So now we can go ahead and end solve this. So go into the calculator here, menu, algebra, end solve. Tan, that looks weird. Tan theta, I'm going to write tan x. Tan theta or tan x is equal to 44.9 over 24.2. Solve for x. In degrees, 61.6764. Okay. Going back to the document, theta is equal to 61.6764 or 2 sig figs, 61.7 degrees. Okay. All right. So we can go on. Oops. There we are. Zing wants to place advertising boards in front of this section of the roller coaster. At 4 positions along the roller coaster track, she records the horizontal distance from O and the vertical height of the track. Her values are shown in the table and represented on the graph. So here we have horizontal distance and vertical distance. At the point 0, we are 3 meters above the ground. At point 20, we are 44 meters above the ground, and so on. Part C asks us to find the total area of the advertising boards. Okay, kind of interesting. What we have here are essentially 1, 2, 3 different trapezoids. And what we could do is we could actually find the area of trapezoid 1, 2, and 3, and that would give us the area. But I think more efficiently, and the way they're kind of like nudging us in some ways, is to use the trapezoid rule to find the area under a function. So that's exactly what the trapezoid rule does. It creates a set of trapezoids that can be used to approximate the total area under a curve. So let's go into the formula booklet, look at the trapezoid rule, unpack it, and then see how we can apply it for this question. All right. So, calculus, and here is our trapezoid rule. Okay, looks kind of intimidating, not all that bad, I don't think. So first off, we start with this h. H is just the width of our trapezoids. So if we have, for example, I'm going to actually approximate the kind of situation that we had right on the previous page. So something like this, and then like this. This h refers to this portion right here, these equal increments along the bottom. This is b minus a over n, essentially end point minus starting point over total number of trapezoids. So when we go back to that question, we'll see this you can use, this h is equal to b minus a over n, but it's a lot easier, I think, oftentimes if we have a visual especially, to just look at the length of these intervals, this bottom portion of our trapezoid. Okay, y naught and yn. Essentially, y naught refers to the height of this first portion. Yn, if there are n number of trapezoids, yn refers to the final height. And then y1, y2, y3, this would be y1, this would be y2. Essentially all of the heights on the inside of our trapezoid, I guess our trapezoids that are bunched together. Okay, and that's really all it is. It looks a little intimidating, more intimidating than I think it really is potentially. So let's go back and substitute here, and we'll find the total area. So if we're going to create some approximation from some starting point of some function f of x, this is some approximation of the area under a curve. Essentially, this is area under the curve approximated by. Then we have this one. We have this 1/2 h, big bracket, y naught plus yn plus, and then we had this y1 plus y2 plus y3 all the way up to whatever the final one was. Okay, let's do it for this function right here. So 1/2 h. H we said was b minus a over n, but we also said that it was just these lengths of this bottom portion of our trapezoid, the height of our trapezoid. There's other videos where I kind of mention why it's height. Essentially, our trapezoids are just rotated 90 degrees. So what would be our height is now our base. But essentially, it's the length of these intervals. From 0 to 20, 20 to 40, 20 to 60. Each time, these are 20. And that's going to be our value of h. All right. I don't think... I'm wondering, I sometimes show a number of different values. A number of different ways to solve this. If you want, and you're more comfortable with the formula, b minus a over n, end point minus starting point over 1, 2, 3, 3 trapezoids equals 20, h equals 20. They're both the same thing. There it is. Y naught. Y naught is the height of this first section right here. So my pen works, there we go. Y naught is right here, and it is equal to 3. Yn is this right here, and it is equal to 30. plus y1, which is equal to 44. Essentially all of the intervals between y1 and yn. And the second one is 37. Okay, so that's it. Length of these intervals is h, starting, ending, all of the middle intervals, 44 plus 37. And this should give us the total area. So let's go ahead and put this into the calculator and we should be good. So before we put this into the formula booklet, actually I forgot to put a 2. So in our formula booklet we have 2 times all of these intervals within this trapezoid. So just modifying that, we have 2 times 44 plus 37 and so on. So y0 plus yn plus 2 times all of the single intervals here. So let's go into the calculator and write this out. So 1/2 times 20 plus, open up double brackets, 3 plus 30, and plus 2 times 44 plus 37. All right, this is good. And we have 1,950. Okay, so writing that out, 1,950 meters squared. So for part C, find the total area of the advertising boards. This would be 1,950 meters squared. Okay. The cost of space on the advertising boards per square meter varies according to the amount purchased. The rate of change in the cost in dollars for space on the advertising boards can be modeled by the function C' of A equals 0.00292A plus 4.71 for A is greater than 60, where A is the total square meters purchased. A company, eByte, wishes to advertise its new gaming device. Zhang tells eByte it will cost $1,750 for 500 meters squared of space on the advertising boards. Part D asks us to find the cost function, C of A. All right, so they've given us this rate of change, or this derivative right here, C' of A, and what we want to do is we want to find the cost function, C of A. So essentially the original function, C of A. So what we can do, usually we have some function, and then we take the derivative to, well, find C' of A. In this case, they gave us C' of A, and we want to find the original function. So in this case, we need to perform something called anti-differentiation. Essentially, we want to reverse the process of differentiation to find the original function. So I'm going to copy down this function here, make some space, and then just work this out a little further down. So C' of A equals 0.00292A plus 4.71. Okay, so I just want to take this. I think we're going to need some space for this. All right, so here's our derivative, and we want to find C of A. Usually what we do is we have some function, and then we take the derivative, we find C' of A. But in this case, we have the derivative, and we want to find the original function. So what can we draw on? Here's our formulas from our formula booklet. We have f of x is equal to x to the power of n. If we wanted to take the derivative, what we would do is multiply this exponent out in front so that it becomes nx. Then we reduce that exponent by 1. But what happens if we want to reverse the process? What if we have fx is equal to xn, and we want to find the antiderivative? And I'm going to call the antiderivative f. So what happens if we want to reverse this process of differentiation? Well, our original process, when we took the derivative, we reduced the exponent by 1. So if we want to reverse this process and go back to find the original function, what we would do is we would have x and we would add 1 to the exponent. Looking at our original, when we had a function, we took the derivative, we multiplied that exponent out in front. If we want to reverse the process, what's the opposite of multiplication? Well, division. We would divide by that new exponent. So once again, you have some function, f of x is equal to x to the power of n, and you want to take the antiderivative. You reverse the process of differentiation. You reverse the derivative taking process. What do? You add 1 to the exponent, and then you divide by whatever that new value is. And that's it. So let's look at our function, and we'll use this, which is given to us in the formula booklet, and we'll find the antiderivative, the original function. Okay, so negative 0.00292a. By convention, if there's nothing alongside our variable, it's a to the 1. So if there's no 2, 3, 4, there's by convention a 1 there. So if there was previously a 1, we add 1, now it's 2. So adding 1 to our exponent, and then dividing by the value of that new exponent. So we added 1, became 2, and we divide by 2. Plus, here we have 4.71, and here we would have 4.71a. Just like when we take a derivative, if this was our original function, we take a derivative, the constant falls away. We want to reverse the process, we would put that constant back. All right. And the last part, which is important, is I want to show you just for some generic function. F of x is equal to, let's say, 3x squared plus 5. If we were to take the derivative of this, what would it be? It would be 6x, and that's it, because the constant just falls away. So when we take a derivative, our constants fall away. And so what does that mean? That means if we've given the derivative, we don't actually know if there was a constant there. There might have been, or there might not have been. But since constants fall away when we take the derivative, we have no real way of knowing what it might have been. So for that reason, we often put a c here to say that there is some unknown constant. So here's our cost function. There's some unknown constant. If we were to take the derivative, constants fall away. So reversing the process, we have to keep this unknown for what might have been here. Okay. So we're close to finding this cost function, but we still have this unknown constant. So I want to actually just clean this up really quick and get rid of this 2, this fraction. So c of a is equal to, dividing by 2, this would be negative 0.0146 a squared plus 4.71 a plus our unknown constant. Okay, so looks good so far. What do we have now? We've got some cost function. We have cost, area, and then some unknown. How can we find this unknown? Let's look to our original statement here. They gave us this information. They said that Zhang tells eByte it will cost $1,750 for 500 meters squared of space. That means when A is equal to 500, C is equal to 1750. So what we actually have is a coordinate point. And if we're looking back at our cost function, we have, I'm going to erase some of this, we have these 3 unknowns here, cost, area, and then our unknown constant. But we actually know 2 out of the 3 unknowns for our original cost function. So if we substitute 2 out of those 3, the cost and the area, we'll just be left with 1 unknown. So the cost is $1,750 when the area itself was equal to 500. And now we went from 3 unknowns to just one equation with one unknown, and we can go ahead and we can end solve this. So let's go ahead and do that. So 1750 equals negative 0.0. Oops, I'm just looking at the document. I put one less 0 than there should be. So just going back to the document here. Going to add that 0 that is missing. So here we have this 0.0292. There should be another 0. So 0.0146. So going back to the calculator again. 1.46, and we have 500 squared plus 4.71 times 500 once again, plus c. Ask the calculator to solve for c. And we have a value of negative 240. Okay. So writing that out, c equals negative 240. So altogether, here's our cost function, and the value of c is negative 240. Okay, so just to summarize, and I guess just go over that process once again, they gave us the derivative, c prime of a, which is the rate of change. We wanted to find the original cost function. So how can we go from the derivative to that original function? Well, we reverse the process and take the antiderivative. This is given to us in our formula booklet. We go term by term, add 1 to the exponent, divide by whatever the value of that new exponent is. So add 1, divide. Remember, constants fall away, but looking at this variable, variables 4.71a, variables fall away, 4.71, and constants disappear. So we would need to add these back if we're to reverse the process. We now have a situation where we have 1, 2, 3 unknowns. They gave us a point on the line, or a point on this function. We can use that to find c, and then there's our cost function. eByte instead wants to purchase the entire space of all 3 boards. Using the cost function from part D, estimate how much this would cost eByte. Okay, so we found this cost function which links cost to area, and we know that eByte wants to purchase the entire space. So essentially this is actually an input-output question. So if eByte wants to purchase 1,950 square meters, how much will it cost? So let's go grab this amount, and then we'll go back to our function. I think this is part E. So part E here, and then here's our amount, 1950. So what is the cost when the area is equal to 1,950? So actually not a bad final question on a paper 2, essentially an input-output question. We have some function, now we want to input into this function to find the output. So let's go into the calculator and work that out. So negative 0.00146 times 1950, this should be squared, plus 4.71 times 1950 minus 240. This gives us $3,392.85. So let's go write that out. $3,392 $392.85. Okay. All right. So 3 sig figs, yes, but I think since it's actually a dollar amount, I often want to put dollars and cents. Okay. I think we're good. All right. So that is the end of the exam. And as always, I hope it was helpful and best of luck. Take care.